So today we are going to talk about section 11.5. We're going backwards right now. Alternating series and conditional convergence. Remember, we already defined what conditional convergence was. Section 11.6, we've done all of that. Much preferred for me to do it in this order. Then we're going to take everything we've done in 11.6 and 11.5, put it together, move it to 11.8. That's where we're heading, where we start adding up infinitely many functions instead of infinitely many numbers. But let's slow down and get back to infinitely many numbers again. Okay, so here's a series, right? We know it's a series because we see this big summation, and we're summing a bunch of numbers, okay? There's really no assumption on these numbers in general. They could be positive, negative, some negative, in some pattern, or not. What is our go-to? What do we do now? When we have series that have some terms that can be negative, our main go-to is test for absolute convergence. That's what we do, right? We got a ratio test, we got a root test for absolute convergence. If those guys don't work, then if we look at the absolute value, we've got our limit comparison tests and geometric series things, and so we've got tests that we can use to test for absolute convergence, right? If absolute convergence fails, then we could converge conditionally or we could diverge, and this is going to help us figure that piece out. So here we are with a series adding up a bunch of terms, right? So our first go-to, ratio test, root test for absolute convergence. That didn't work. Now what? Okay. Well, if that didn't work and you didn't get absolute convergence, then you better hope you have an alternating series. That's what this section is about. Because otherwise, there's really not a lot other than be clever. Okay? So what is an alternating series? Okay? So what is an alternating series? Well, exactly as the name suggests, it's a series that alternates positive, negative, or negative, positive terms that it's adding up, right? Okay, so if we wanted to write down some examples of an alternating series, what it would look like, we would have, say, the sum. I'll just try to do this the same way I've done it here. N equals 1 to infinity. One way to do it, we'll just start counting at 1 of our ANs. They would look like sum n equals 1 to infinity of maybe, how do we make something alternate sign? Good, you got it. Minus 1 to the n minus 1 is what I'm going to start with, right? Bn. So what would this guy look like if we wrote out the terms, right? When n is 1, we have negative 1 to the 0, which is, good, 1. So b1, right? When n is 2, this guy will be negative, so minus b2. When n is 3, that guy will be, right, 3 minus 1, 2 squared, even, right? So that'll be positive, so it'll be plus b3, right? Oops, 3. When n is 4, right, that'll be odd, right? 4 minus 1, 3. And so what do we have? Minus b4. Yeah? Alternating series where, right, the b sub I are all positive. So b1, b2, b3, b4, they're positive. The sign change is happening here with this guy, right? Does that make sense? So that's an alternating series if it looks like that. Or, right, if your series n equals 1 to infinity, an looks like, it could start alternating first negative and then positive, right? Okay, how would we do that? Well, the simplest way to do that is just minus 1 to the n, yeah? Okay, so if we have that, then the very first term is negative, so it's minus b1 plus b2 now, because when n is 2, that's positive, right? Minus b3 plus b4 minus on and on forever, right? Yeah? Okay. Just double checking that we're videoing here. Okay, let's see. Woohoo! And so here we are. And again, it really doesn't matter what these guys are, right? This could be, minus 1 to the n minus 5, right? If we had that and we started counting at n equals 1, right, then that would be negative 4, and that would still be 1, so we'd really be up in this case, right? Does that make sense? Okay, good. It could be minus 1 to the n plus 1, right? Okay, it doesn't matter. So that would be this case up here, right? Could be minus 1 to the n plus 1, right? It doesn't really matter as long as we have an alternation every time n changes sign. Yeah, does that make sense? Okay. What about this? Would this alternate? What if it was minus 1 to the 2n? Would that alternate? Good. No, right? We couldn't replace either one of these guys by minus 1 to the 2n. Why? Because that's always just equal to 1, right? 2n's even. Negative 1 to the 2n's always just positive 1. That wouldn't alternate, right? What's another one that wouldn't alternate? You got it. Minus 1 to the 2n plus 1, right? Or 2n minus 1, right? Also no, right? Because this guy is good. Odd, and negative 1, it's an odd power is always negative 1, right? That wouldn't alternate either, right? Okay, those guys alternate. Point that out because you'll run into these things later and you'll have to realize what alternates and what doesn't. Yeah? Okay. All right, alternating series. We get it. Yeah? We got the idea. Okay. So what's going to help? What's going to help us? Let's look at a couple of examples of particular series that look like this. Okay? So maybe let's look at, for example, here's a classic. Here's a classic example. And it's called the alternating harmonic series. The alternating harmonic series. Okay, well, what's that guy going to look like? Okay, we're going to be adding stuff up, and what are we going to be doing, right? We're going to be adding up 1 minus a half, right? Plus a third, right? The harmonic series is 1 plus a half, plus a third, plus a fourth, right? Whoops. So the alternating harmonic series is going to alternate sign, plus, minus, plus, minus, plus, minus. Does that make sense? That's the alternating harmonic series, yeah? Okay. So what are our b sub n's for the alternating harmonic series, right? Well, it's just 1 over n, right? Yeah. Okay. So the harmonic series is this guy with pluses everywhere, and the alternating harmonic series is this guy with our alternating guy here, right? Okay. Notice here the b sub I are 1, 1 half, 1 third, 1 fourth, 1 fifth. Those are all positive, right? Okay. So that's an example of an alternating series. What's another example of an alternating series? Now, we haven't said whether or not this guy converges or diverges. We just said he's an alternating series, right? Okay. Another example is 11.6, number 31. Let's look at that guy. That is minus 1 to the n times, and this one actually is going to start counting at n equals 2. And that is minus 1 to the n divided by natural log of n. Okay? So what is that guy? When n is 2, that's positive, so I have 1 over the natural log of 2. When n is 3, it's negative, so it's minus 1 over the natural log of 3, plus 1 over the natural log of 4, right? Minus 1 over the natural log of 5. Make sense? Got it? Okay. All right, so both of these series are alternating series. The actual terms, 1 over natural log of 2, and 1 over natural log of 3, 1 over natural log of 4, those are positive terms, and then we're just adding and subtracting, right? The negative is coming from there, and it alternates each term. All right, so now our question becomes, well, what about these series? You know, do they converge or diverge, right? Well, what is our go-to? Our go-to is like check for absolute convergence, right? Okay. our first go-to for any such series is, does it converge absolutely? That's our question, because if it converges absolutely, life is great, right? Absolute convergence implies convergence. We proved that. And so if we change all the positives and negatives, right, and it converges, then we know this guy converges. Well, tell me about this one, right? Does this guy converge absolutely, right? So the alternating harmonic series does not converge absolutely, right? Why? Because the sum of its absolute values, right? If I look at the sum of the absolute values of this guy, that's just what series? The harmonic series, right? That's where the name came from. And this guy diverges, we know, because he's a p-series with p equals 1 and p equals 1 diverges, right? Okay, so the alternating harmonic series does not converge absolutely, but it still might converge conditionally. We don't know. Or it might diverge, right? Okay, so again, what do we know? When we're asking the question now, right, converge or diverge, converge now has two things, absolute convergence or conditional convergence, right? Okay, it's one of those two guys. Which one? What we just ruled out for harmonic series is it doesn't converge absolutely. So it might converge conditionally, which means converges. This guy would converge. It just if we change the negatives to positives, it doesn't. That's the absolute piece, right? That doesn't work. Or it might diverge. We don't know. We need help. We don't have anything yet to test that. Okay, so this guy does not converge absolutely. What about this one, 11.6, number 31? Well, this one was one that you actually did in 11.4. So this guy, if we test this for absolute convergence, then what would we get, right? We'd be looking at the series sum n equals 2 to infinity of just 1 over the natural log of n. Yeah, that guy would just be positive if we're going to test that guy for absolute convergence. And what happens? This is actually problem number, this is section 11.4, number 41b. You've already done this problem back when you did 11.4, and in that one you used the limit comparison test, case 3. Since it's case 3, you know what happens, right? To show that what? This series diverges. Okay? So when we change all the positives to negatives, that series diverges, and therefore this one is also not absolutely convergent. So this guy's not absolutely convergent, and this one is not absolutely convergent either. Okay? But our question is, we can't say that that diverges. It still could converge conditionally, or it could diverge. So we need another test. Okay? We need another test. Let's look at one more series before we, we'll come back to these guys. Let's look at one more example. Let's look at example 3 in this section, what do we have? We've got the sum n equals 1 to infinity of cosine n over n squared, right? So what is that? Well, when n is 1, that's cosine of 1 over 1, right, squared, plus cosine of 2 over 2 squared, right, 4, plus cosine of 3 over, what, 3 squared, 9, plus cosine of 4 over 4 squared, 16, right? We'll write out a few more. Cosine of 5 over 25, you got it, plus cosine of 6 over, good, 36. Okay, one more just for fun, right? Plus cosine of 7 over 49, nice. Okay, goes on and on forever, right? You don't see a plus or minus 1 in there, right? Well, are these terms all positive? Well, in fact, no. Okay. All right, so if you check, cosine of 1 is positive, but cosine of 2 and 3 and 2 and 3 and 4, those guys are all negative, so it's positive plus a negative plus a negative plus a negative, and then these guys are positive plus positive, 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 and then there's more negatives and positives that keeps on going, but it's not any type of pattern, right? So there's positive terms, there's negative terms, but it's not the alternating pattern, right? Okay, so this is not an alternating series, not an alternating series, and so this is example 3 and 11.6. So you should go there to see the solution, right? This guy is absolutely convergent. And what do? We use the comparison test, okay? We use the comparison test to show that this guy is absolutely convergent if we look at its absolute values, right? Maybe you already see what we need to do, right? Because I know that the absolute value of cosine of n is always bigger than or equal to 0 and less than or equal to 1, right? And therefore, that over n squared is bigger than that. It's smaller than that, and we know this is a convergent p-series, so that guy converges. So we have absolute convergence for this guy, and we're super happy because if we didn't get absolute convergence, we'd have been completely out of luck. We wouldn't have, it's not an alternating series, so we wouldn't have another test for conditional convergence. Does that make sense? Okay. It would have been, be clever. Okay. All right. So let's keep going, right? So what do we do when we do have an alternating series and that alternating series is not absolutely convergent? Then we're looking for conditional convergence. Yeah? Okay. So for that, we'll use the alternating series test. Okay, the alternating series test. So what does the alternating series test say? It says let the sum of an be an alternating series. We just defined what that was, right? Let that be an alternating series. And then, basically it says, if the b sub n's, right, those are the positive piece, ignoring the plus and minus, right? If the b sub n's are decreasing, if the b sub n's are decreasing, right, and this is kind of like, duh, okay? The limit as n goes to infinity of b sub n is equal to 0, right? Okay, well, why? Like, if that limit isn't 0, then the divergence theorem, the divergence test would have said that this guy diverges, right? Okay, so anyway, you should have caught that before you got there. Yeah. Okay. Anyway, so we need both of these. There's really two things, right, that you check, that and that, right? But if that's violated, then the divergence test is immediately going to say that the series diverges. Okay. So if the BNs are decreasing and that limit is 0, then the alternating series is convergent. And remember, conditional convergence means convergent, just not absolute convergence, right? It means the series converges, just doesn't converge when you change all the negatives to positives. Okay, so that's our guy, right? So that's in words, and so if we think about the alternating series test, okay, that's what we'll call this guy AST, right? Alternating series test. So if we just shorthand it a little bit, you have an alternating series, right? With BNs are decreasing. Well, we have a couple of ways to say that. The next BN, right, the next guy is smaller than, right, or equal to, let's just stick with smaller than the previous guy, right? Okay, the next guy is smaller than the previous guy. Or, right, we can turn that into a function of x and take its derivative and look for that derivative to be negative, right? Okay, then we have decreasing. So we have an alternating series with this being true, that or that, right? And this limit, I'm just referring to the ANs and the BNs from the previous whiteboard, and this limit is 0, right? Implies convergence, right? That's the shorthand version. Okay, so let's go back to our examples. So let's go to number 11.6, number 31 first. Okay, so that one again was the sum n equals 2 to infinity of minus 1 to the n over natural log of n. Yeah? Okay. What is Bn for this problem? Bn is 1 over the natural log of n, right? We know this guy does not converge absolutely. We've already ruled that out, and so therefore we need to now test for conditional convergence. Okay, we have to identify the BNs. We now want to determine, so it is an alternating series, do the BNs decrease, right? A couple of different ways to do that, but let's just do this piece this time just to get some practice with derivatives. So let's look at B as a function of x is 1 over the natural log of x, right? And that would be the same as the natural log of x all to the negative 1 power, yeah? So let's take the derivative, a little practice with derivatives. What is B prime? Stuff to the negative 1, what do? Bring down the power, leave the stuff alone, right? Subtract 1 from the power, very nice. Then what? Multiply by the derivative of stuff. What's the derivative of natural log of x? Good, 1 over x. Let's just write that a little bit nicer. So what do we have? Minus 1 over x times the natural log of x quantity squared. Exponents, right? What's beautiful about that? Top is negative, the bottom is positive as long as x is greater than 1, right? Okay, so negative, positive, negative over positive, so this is less than 0 for x greater than 1, right? Natural log of 1, 0. Okay, so is x greater than 1? Yes, because n starts at 2, so we changed it into x, so we're good to go. So therefore, right? What? B is decreasing. BNs are decreasing. We justify that piece. That's really the important piece, right? And then we ought to just, at least note that we've checked this limit, right? The limit as n goes to infinity of Bn, 1 over natural log of n, right? Okay, natural log's going off to infinity, growing unbounded. As n grows unbounded, 1 over something growing unbounded is 0, right? Okay, again, if that hadn't been 0, divergence test would have told us that guy diverged, okay? So there we go. What did we just discover then? Therefore, this series is conditionally convergent. converges conditionally. The series converges, it just doesn't converge if you change the negatives to positives, right? Okay? Not absolutely convergent, but conditionally convergent. Well, that's cool, right? Okay? Let's go back to our alternating harmonic series. Yeah? I can erase this because we have our shorthand version right there. Oh, we're not going to prove the alternating series test. Read the proof in your book. We just don't have time. Okay? We've lost so much this semester. But the proof in your book is very readable. So you can read that just so that you have confidence that this is a true thing. Yeah? All right. Back to the alternating harmonic series. We know the alternating harmonic series does not converge absolutely, right? Because it's that series of absolute values is the harmonic series, which is the classic divergent series. All right, so what was this guy? Sum n equals 1 to infinity of minus 1 to the n minus 1 times 1 over n, right? Is that what we were using it for with? Yes. All right, so does this converge conditionally? Right? We already know it does not converge absolutely. So what do? What's the Bn here? Well, Bn is just 1 over n, right? It's just this part, ignoring the sign change piece, yeah? Now let's do the other one, right? Okay, that's pretty simple, right? B sub n plus 1 is not hard. B sub n plus 1, right, is 1 over n plus 1, yeah? And 1 over n plus 1 is strictly less than 1 over n, right, which is our B sub n. Why? You got to convince me you understand why, right? So you got to say, right? Why do you know that that fraction is smaller than that fraction? Because we've got the same numerator, right? It's the exact same numerator, 1, with this guy has a larger denominator. A larger denominator gives a what? Good smaller fraction. You gotta say, you gotta convince me. Okay, just like down here, you gotta take those derivatives and show it negative. All right, and so this is legit. This is what we had to show. And what else, right? Oh, that limit as n goes to infinity of bn 1 over n. What is that? Who thought of our favorite limits? We've seen that 1,000 times. That limit is 0, and these guys are decreasing, and therefore, what do we know? We know that the alternating harmonic series is conditionally convergent. So that does not converge absolutely, but it does converge conditionally. It converges, just not if you change the negatives to positives. Right? That's super cool, right? Let's do one more. Yeah? Okay. What about this one? What about that one? What would you do? What would you do? Oh, I think I heard it. You would say, hey, this converges absolutely. Done. Right? This does not require the alternating series test. Are we good here? We got that? Right? So this converges absolutely. Why? Right? Why do you know it's absolute convergence? Because if I look at the series of absolute values, I ignore that guy, and I'm thinking only about that guy. And what is this? This is the P series. And P is what? Good, 2. And 2 is what? Bigger than 1. And that's when P series converge. Right? Yeah? Okay. So, This one does absolutely not require alternating series test. Does that make sense? No AST. Yeah? Because it's conditionally convergent. Period. Right? Therefore it converges. Right? Change the pocket. Sorry, it's absolutely convergent. Therefore it converges regardless of whether we have positives or negatives. Right? We can change all the negatives to positives and it converges. Right? Converges absolutely. You can leave it alone and have it alternated sign. Still converges. Right? Make sense? Okay. But we did not need the alternating series test to determine that. Yeah? Okay. Good. All right. What else is the alternating series going to give us? It's going to give us some interesting, some simple, easy error bounds. So let's look at that. Okay. All right. It's just to see if you were paying attention, right? You don't just go to AST just because you have an alternating series, right? This guy is going to be fun, actually. We'll talk about that kind of at the end. This is crazy. So the harmonic series diverges, but the alternating harmonic series converges, right? Okay. That may sound crazy. It gets even crazier. You'll see in a little bit. Alrighty. So let's see. So convergent alternating series also give us an easy error bound to guarantee how close, right, that's what an error bound does, it guarantees how close an approximation is to the actual sum, right? That's what an error bound does. What's an approximation? It's a finite sum, right? You can't add all infinitely many terms, right? It's only for geometric series that we have those nice little formulas, right? So an approximation is a finite sum. You can always add finitely many numbers, right? Especially with a computer, all right? Okay, so what is the actual sum, right? It's the S guy, right? It's the actual, sum n equals 1 to infinity of your alternating series, right? Okay? That's an alternating series, yeah? Where an is either minus 1 to the n minus 1 times bn, or minus 1 to the n times bn, or something else that alternates, right? Okay? Okay, so, well, why is this error bound easy? Okay, well, let's just look at a simple example. Okay, so let's consider the example where we have the sum from n equals 1 to infinity of minus 1 to the n minus 1 times bn. Okay, so if we do that, when we start counting at 1, we just have b1, right? And then the next guy is minus b2, and then plus b3, and then minus b4, and plus b5, right? On and on forever. Yeah? Okay. So, let's start looking at the partial sums, right? Again, what is this? Right? This is the limit as n goes to infinity of the nth partial sum. What is the nth partial sum? The sum first n terms, right? Okay, so let's look at S1. S1 is just B1, right? What's S2? S2 is B1 minus B2, right? Okay, now let's think about it, right? The BI's are all positive, right? Okay, and they're decreasing, right? Because we have a convergent alternating series, yeah? Okay, so B2 is smaller than B1, right? Okay. What's S3? S3 is B1 minus B2 plus B3, right? Yeah? Okay, so this guy, if I think about this, right, I took some positive amount away from B1, so that's going to be smaller than S1 was, right? Okay? Now this right here is S2, right? And now I'm adding B3, right? Okay? And so that's positive, so that's going to be bigger than S2, yeah? And then S4, I'm going to do B1 minus B2 plus B3 minus B4, right? And this guy is S3, right? And I'm going to take some away, so this is going to be smaller than S3. Yeah, does that make sense? Okay? So what's kind of going on there as we're doing that? If we just kind of draw, right, an axis N, right? And, you know, so here's maybe, say, S1, right? So that's S1, yeah? That's like our first approximation. Approximation to this sum with one term. Probably not a great approximation, right? Okay? And then I get two terms, right? S2, and I'm going to come down some, yeah? And these guys are all positive, but they're decreasing, so I'm going to, you know, maybe be down here, yeah? Okay? I won't go across, all right? And so, so for S2, right, then I'm like down there, yeah? Does that make sense? Now, S3, what? It's going to be bigger than S2, right? Because I'm going to add something positive. But not as big of a distance as I had here, right? Because B3 is smaller than B2, right? Okay? And so, you know, S3 is going to be like up there. Yeah? Does that make sense? Okay? And then, what am I going to do when I compute S4? I'm going to now take away B4, right? So I'm going to be smaller than S3. S4 is going to be below S3, but it's going to be above S2, right? Okay, does that make sense? So you're kind of seeing that what's happening right now. So then we have like S5, right? And then S6, yeah? And so basically, right, our S is going to be somewhere in between there. Does that make sense? Is that, do we kind of get what's happening there? Okay. So let's write that out just in math now. We have our visual. Okay. Remember, this is just in that one particular case when we started with a positive B1, right? So we're just doing this as an example. So the idea here for this example is what? Well, our guy S, right, that we're trying to hone in on, well, he starts off, right, between S2 and S1, right? So in this case, S2 is smaller than S and S1 is bigger, right? Okay? And then at the next step, right, at the next step he was between S3 and S4, right? But this time S3 was bigger and S4 was smaller. Yeah? Does that make sense? You got there? And then the next time, right, he's between two more partial sums, but this time S5 is bigger and S6 is smaller. Does this make sense? Okay? All right. Oh, I skipped one. Whoops, I skipped several. Let me just stick the other ones in there, right? So let's just do between S2, right? So here is between S2 and S3, right? So, yeah. So, okay, good. The next one, yes. So S2 is smaller, S3 is bigger, right? Then S3 is bigger, S4 is smaller. Yes? Right? Comparing those two. So this is comparing S1 and S2, S2 and S3, S3 and S4, S4 and S5, right? S4 is smaller, S5 is bigger. Make sense? Does that kind of make sense? Okay. All right. So basically, what is this kind of saying? All of these guys are saying that the actual sum, right, the actual sum, which is S, is always trapped between any two, right, successive partial sums. Right? That's kind of the deal. So since we've got that, let's now just say something in general. Right? Now remember, what is S? It's the nth partial sum plus the remainder, right? The remainder is the error, right? This is the sum of the first n terms, k equals 1 to n of a sub k, and this guy is the sum of the rest of them, right? K equals what? N plus 1 to infinity of a sub k, right? The rest of them, yeah? Okay? This guy's the error. It's also an infinite sum, okay? So we've done this before, right? Now you're getting scared because when we did this before, the error bound with integral test, that was a lot more ugly and it was a lot harder to deal with. This one's a little bit simpler. So same deal though, same thing that we did. Let's look at the difference between the actual value and the approximate value. That's Rn, right? Okay? And let's look at the absolute value. So it's just the distance between them. We don't care whether we're bigger or smaller. We're just want to know how far apart they are. And what did we just say? Well, we just said that, so the distance between, right, the sum, since S always lies between the any two successive partial sums, then the distance between this and another sum has got to be smaller than the distance between the two successive partial sums, right? Okay, the distance between that guy and that guy is smaller than the full distance between any two, yeah? And so we'll say that's smaller than S sub n plus 1 minus S sub n, okay? But what is S sub n plus 1 minus S sub n? Remember, Sn is the sum of the first n terms, right? Okay? Sn plus 1 just adds the next term, right? So that would be a sub n plus 1. But what is a sub n plus 1? Well, it's plus or minus b sub n plus 1, right? And since we're here in absolute values, right, we don't care about the plus or minus, and so we get our b sub n plus 1, right? It's just the next term that got left off, yeah? Well, that's kind of awesome, right? So what does that tell us? Okay, therefore, we really want this piece. The distance between the actual infinite sum, right, and a finite sum of the first n terms is always less than or equal to just the absolute value of the next term you left off and didn't count. That's super cool. Let's see how that gets used. It gets used in a variety of ways. For alternating series. Only alternating series, right? Not if you don't have an alternating series. Okay, so let's go back to our alternating harmonic series. Okay, what was it? It was sum n equals 1 to infinity. I'll write it here, an. What were our an's? Sum n equals 1 to infinity of minus 1 to the n minus 1 over n, right? So what are our bn's? So what, we'll write it out again just so that you see what these guys are, right? It's, when n is 1, right, we get 1, and then it's minus 1/2 plus a third minus a fourth plus a fifth minus a sixth, right, plus a seventh, right, minus an eighth plus on and on forever. Yes? This is the alternating harmonic series. Yeah? What are the bn's for this guy? 1 over n. Good, right? We don't care about the alternating piece, the minus 1 to the n minus 1. So the bn's are 1 over n. Yeah? All right. So let's suppose, right, let's see how we could, one way to use this guy, right? If we add up all of these guys, the first how many terms? Get the first 7 terms, right? This would be S sub 7, right? Now, that's not so hard to do. You could do it on a calculator if you needed to, right? I wouldn't want to make you do that, right? But that's simple, simple enough. You're adding up 7 fractions, yeah? Okay. So we can come up with a number from that, S sub 7, yeah? So what does this say then? The actual value of the sum of this infinite series, if we keep going on forever, plus 1/9, minus 1/10, plus 1/11, minus 1, right? Yeah? Okay. The difference between that and just adding up the first 7 terms has got to be less than or equal to what? Well, b sub 8, n plus 1. Here, n is 7, right? Yeah? Okay. N is 7, right? N plus 1 is 8. Well, what is b sub 8? B sub 8 is plain old 1/8, right? Not the negative, right? This is absolute value, right? We don't care about the b's are positive, right? So it's just plain old 1/8. What is 1/8? 0.125. So you know that if you add up the first 7 terms, you're within 0.125 of the actual sum, right? That's kind of cool, right? To just know that immediately. It's super fast. It's just the absolute value of the next term, right, that you left out is your error bound in alternating harmonic series. And that's pretty simple, right? So how else do we use this guy? In the same way that we used other error bounds, we use it to help us know how many terms we need to add up in order to guarantee a certain error tolerance. So suppose instead, right? So suppose instead we want to know how many terms of the alternating harmonic series we need to guarantee that the nth partial sum, right, Sn, what is n? That's what we're asking. How many terms? What should n be? That the nth partial sum is within 10 to the negative 6, right, of the actual sum, which we don't know, right? Okay. So what would we do? How would we do this? We would utilize this idea, right? So what does this say? This says that now the distance between S and Sn, right, is less than or equal to b sub n plus 1. What is b sub n plus 1 for this guy? 1 over n plus 1, right? We know that that is going to be true. And so we want that to be less than 10 to the negative 6, right? Okay? This is the distance between the actual sum and the nth partial sum. So if we know it's less than this and we want it to be less than 10 to the negative 6, then what should we just do? Yeah, force that to be less than 10 to the negative 6. And now do what with this guy? Solve for n. This one isn't so hard to solve for n, right? Let's do that. If I multiply both sides of this inequalities, I don't want this piece in the box, right? So if I multiply by 10 to the 6, I'll get a 10 to the 6 on the other side. And if I multiply by n plus 1, everything's positive, right? So I don't have to change the direction of the inequality. I get an n plus 1 on this side. And so therefore, what does that say? N has to be greater than 10 to the 6 minus 1. But n has to be an integer, right? And so if n is going to be an integer that's greater than 10 to the 6 minus 1, then n should be greater than or equal to 10 to the 6th, yeah? What is that? A million terms, right? Okay? That's how many we need to be within the 6 decimal places, yeah? Okay? what if we instead ask the question, same question for instead this guy, our 1 over n squared guy. So now our bn is 1 over n squared, and now instead what are we adding up? 1 plus, minus a fourth plus a ninth, right? Plus minus a 16th, right? So 1, 2, 3, 4, when n is 4, that will be negative, and that will be 16th, right? Plus 1/25th minus 1/36, right? You get it. On and on and on forever. Yeah? What if we add that up? We can already see, right, you need less terms in order to be like closer, right? So in order to be within 1/8, right, we only need the first 2 terms, right? That's kind of cool, yeah? That's pretty awesome, right? Crazy, super crazy, right? 3/4 is within 1/8 because it's within 1/9, right? That's pretty cool. But what if we want to guarantee, right? Well then, how would this change? It's all the same, right? Except for what would b sub n plus 1 be now? For this problem, 1 over n plus 1 quantity squared, right? Just because we don't use the alternating series test to test this guy, because it's absolutely convergent, right? That doesn't mean we can't use this error bound, right? And so now our error bound, I mean, you can use the alternating series to test this guy, but it just doesn't make any sense. It just takes way more time, and it just doesn't make any sense. All right, but anyway, so here we are. Now you're here, right? And you're going to do the exact same thing for this series, right? For the series below. Series below, right? And now we're solving this guy for n, and now what do we see? 10 to the 6 is less than n plus 1 quantity squared, right? So n plus 1, since everything's positive, is greater than 10 cubed, yeah, right? Yes, y'all with me? Okay, so n is bigger than 10 cubed minus 1, or n is greater than or equal to 10 cubed, which is just 1,000. That's way better than 1,000,000 maybe, right? Okay, so we get that kind of accuracy for the sum of this guy with only 1,000 terms. That's pretty cool, right? Super simple. Not maybe the tightest bound in the world, but very simple, okay? Simple sometimes is nice. Well, let's see. What else? Is there anything else I want to say about that? Back to the guy, the alternating harmonic series for a sec. Okay, so now let me just erase this. So this series, remember this one is which? Absolutely convergent, conditionally convergent? Good. Absolutely convergent, right? Because in absolute value, we had a p series of 2. So we could call this the strange nature of conditionally convergent series. Okay, so our guy n equals 1 to infinity of minus 1 to the n minus 1, 1 over n, our alternating harmonic series, which does what? Converges conditionally, which means converges, right? Okay? This guy converges absolutely, this guy converges conditionally. This alternating harmonic series right? That guy is conditionally convergent. This guy has a sum, and its sum is what it is. It doesn't really matter. What we do with these terms, conditionally convergent series are a little nutty. So you can go and read about this at the end of section 11.6. It is page 742. Maybe this will inspire you to take a little more math, right? Essentially, one of the things they talk about there is you can rearrange the order of the terms in a conditionally convergent series in order to make the series add up to anything that you want it to add up to. What? Yeah, super nutty, right? You wouldn't believe it, except for Riemann proved it, okay? So it's pretty crazy and pretty nutty. And so we have both these series are this one's conditionally convergent, this one's absolutely convergent. They're both convergent, right? And we're adding up infinitely many terms. And remember, what did we start off class in January talking about, right? You can't just make assumptions when infinity's in the game, right? Okay, there's crazy things that can happen that are beyond our common sense. And that is what is true about these nutty series, that we can take this guy, rearrange the terms, and make it add up to any number, any real number that we want it to add up to. And we can come up with a rearrangement such that partial sums will show that it goes to that. And that's pretty crazy. So all convergent series aren't created equally. All convergent series don't work the way our finite mind works with adding things up, which is, again, another reason you need math to help you find the path, right? Math for the path, and math for the power as well. That's where we're heading. 11, we're done now with this. Section 11.8 is where we're jumping. That's where our next lecture this week will be, and that is where we start talking about power series. So math for the path, math for the power. See you soon.